So one thing we're doing is finding arc length. Right? There's some parameterization, right? You have some parameterization of a curve, right? It's a finite curve of, on a fixed time, right? And we have some formula for the arc length. And that formula is pretty simple, right? The length is going to be the integral from a to b of
the magnitude.
Yeah. Right, the magnitude of the tangent vector, right? In other words, the speed, right? The magnitude of the velocity vector, that is to say the speed. Okay. And then from there, we went to somewhere else, right? We're looking at this thing called the arc length parameterization, right? And how do we get the arc length parameterization? Who remembers this? Peter.
There's just like that integral, but instead of a to b, it's 0 to t.
Okay, so that's the arc length function, right? We first create the arc length function, right? That's this guy, sigma of t, the integral from a to t of the speed, right? And when usually, one has to, use a different variable. You don't use t here because then you don't know. It's a little bit confusing as to the t here and the t here. So I'm just gonna avoid putting the variable in. Okay. Okay, you're right. And then we use this thing to create the arc length parameterization. What's the arc length parameterization? How do we do that? Melissa?
Take the inverse.
Take the inverse function, right? So this guy from a to b gives us a function to 0L, right? Sigma is a function from ab to 0L, right? At time b, it says, oh, you've traveled L units, namely the entire arc length, right? And so we take the inverse function, right? So this is our t variable. Let's call this, let's say that the variable for this real line is s, right? And then what do we do with it? What do we do with that inverse function? We
plug it back into the original r.
Plug that thing into the original r guy, and we create a new function p. We get a new function p of s, namely r of sigma inverse of s. Right? And that guy is the arc length parameterization. That thing gives you the arc length parameterization of your original curve. Right? So maybe I should write that this thing parameterizes some curve in R3. Okay. So this thing is a map onto this curve C, which lies inside R3. Okay. Right. And so that's where we stopped. Right. The arc length. So this is the arc length function here, and this thing here is the arc length parameterization. Arc length parameterization. Okay. So okay, and we said that the good thing about the arc length parameterization. Sorry, Flo, you always dress nicely and then cover yourself with a huge jacket. I guess it's cold. No, it's just sort of amusing. Okay. We said the good thing about the arc length parameterization is what? Flo.
It creates a unit tangent vector.
Right. So the tangent vector of the arc length parameterization turns out to be a unit tangent vector, the unit tangent vector, right? And so that tells us that the tangent vector, the velocity vector, is a unit velocity vector. In other words, the speed of this parameterization is 1. Okay, the speed of this parameterization is 1. Okay. So now we can go to the second important notion in this section, which is curvature. Okay. So definition, we define the curvature of the curve at the point P of S as it's denoted with a kappa which is basically a k, as the derivative of the unit tangent vector with respect to the arc length parameterization. Okay. The derivative of the unit tangent vector with respect to the arc length variable, the arc length parameterization. Okay, that is, you have to figure out things you have to figure this stuff out with respect to the arc length parameterization, and then differentiate it with respect to that with respect to that parameter. Okay, and the reason is this. For curvature, the scale matters. For curvature, the scale matters. If I drew a gigantic circle here, like a gigantic circle on the Earth, radius 1 mile, then to me that would then we'd like to say that that has a very low curvature, right? Because as you're walking along it, it seems like it's a straight line, right? It has low curvature. But if I have a tiny circle here, right, a really tiny circle, then for me that should be for us we want to say that that thing has greater curvature than the big one, right? Because that's a very, very fast turn for us. Okay. So the idea of curvature that we want is one in which scale matters, right? Because those circles are the same circle, right? If you discount scale, then those circles are the same thing. But we want to include scale, and so we say we're going to differentiate with respect to the arc length parameter, which ensures that that scale is included, right? It forces, because the arc length parameter will say, well, you're turning really fast with respect to this. If you're traveling along the curve at a rate of 1 unit per 1 unit time at a speed of 1, then you're turning pretty fast, right? Or if you're or at a speed of 1, this doesn't seem to be that fast. It's got a low curvature, right? So the arc length parameterization basically incorporates the scale into the definition here. Okay, that's why you differentiate with respect to that, rather than to just any variable. So okay, so yeah. So it's so this is the blah, which is the magnitude of the rate of change of the unit tangent vector with respect to S, the arc length parameter. So that's the K. Differentiate with respect to x. Okay. So just one remark. If we take P and differentiate it, what do we get? If we take the arc length parameter, recall what was the derivative of the arc length parameter, arc length parameterization? You've already said it. You've just gotten confused by all the words, right? Take the arc length parameterization. You take its derivative. What do you get? What was special about the arc length parameterization? You get the unit tangent vector, right? So you get the unit tangent vector. So if I take the second derivative, right, then I get this thing. So the curvature is the magnitude of the second derivative of the arc length parameterization. Just to keep things straight. Right, so curvature is going to be the magnitude of the second derivative. Okay. So here's the example. Somebody gives you a circle, a cosine t, a sine t. Okay. A circle of radius a, where a is some positive number, right? And it says, what's the curvature of a circle? What's the curvature of a circle? So maybe I'll ask you to spend 1 minute and see how far you can get. Yeah. Or maybe 2 minutes. And I'll hand back some homeworks while it's happening. Okay, so somebody tell me what we need to do. If we're going to find the curvature, what's the first thing we need to do?
Take the derivative.
Take the derivative? Why take the? So you're going to take the derivative of. Okay. I'm sorry. So so to find the curvature, what we want to do is take the derivative of the arc length parameterization. Okay. So the first thing we want to do is actually go for the arc length parameterization. Okay. So how do we do that? Find the arc length function. Right. So the arc length function is going to be this thing, the integral from say 0 to 0 to t of the speed of this guy. Oh, okay. So that's is that what you're talking about? Take the derivative. Yes. Thank you. Sorry. Yeah. So we take the r prime is going to be a negative a sine t, a cosine t, right? And we're going to take the magnitude of that guy, right? And what's the magnitude of that guy? A, right? Right, A. Right. And so we end up with A2. Right? Right. So the inverse function then is going to be what? Lily? T over A, or I'm going to use S because I want to use a different variable. Right. I mean, you could write. Certainly, it makes sense to say that the inverse function does this sort of thing, right? It takes your input and then divides it by A. But I don't want to confuse my variable here with my variable here, so I'm going to use S for that. Yeah. Okay. So okay, and then what? Then what do? You create your arc length function, arc length parameterization by just. Is it too obvious? Maybe it's too obvious. Alana, tell me what to do.
Okay, I got a little behind. What are you?
Oh, that's okay. So we've just looked at the inverse. We've just found the inverse for the arc length function, right? And how do you make the arc length parameterization out of it?
Oh, don't you, so don't you put that in for t?
Yeah, you just plug that in
Yeah.
as the input, right? So it's going to be r of sigma inverse of s, namely a cosine s over a, comma a sine s over a. Okay. And then you take two derivatives of that, right? So one derivative with respect to s, right, gives me Right, so two derivatives will end up with negative 1 over a cosine s over a, negative 1 over a sine s of k. And so the curvature at time s is what?
Magnitude of that.
The magnitude of that, which is
Square root. That squared plus times
this squared plus that squared, square root of that, and so in the end you end up with what? 1 over a. Right? So you end up with 1 over a. Right? Because this thing, cosine, sine, cosine comma sine, you know, is a unit is a unit vector, right? So you multiply a unit vector by this constant, so the size of the vector is going to be just the magnitude of that constant. Okay. Okay. So that gives it to us, right? The curvature of a circle, of radius a, is constant. You know, that's what you might expect. The curvature is a constant. You know, the curvature is the same wherever you're standing on this unit circle, and the curvature is 1 over a. The curvature of a circle of radius a is 1 over a. And so if your radius is huge, what does that tell you? Your curvature is small. And if your radius is tiny, then your curvature is huge, right? And that's what we wanted, right? You know, for a tiny circle, and then it should have a gigantic curvature. For some reason, my son, who is 3, keeps on singing about tiny circles. So that's why I keep on smiling when I say tiny circle. But yeah, it's like his song of, I guess he's sort of stopped now, but a week or two ago, he kept on walking around saying, tiny, tiny, tiny circle. So, yeah, it's not clear what he means by it, but yeah. Yeah, it's not a mathematical. I'm pretty sure it's not a mathematical observation. Our nickname for him is Mr. Random. Yeah, because he just blurts out these sort of random things. Okay, so curvature of a circle, and in fact, this is sort of an alternate way that you can approach the notion of curvature. So somebody gives you a curve and says, what's the curvature at that point? Okay. What you do actually is you could think of it like this, that the curvature tells you, you take a circle that matches the curve there, that is what's called an osculating circle. You create an osculating circle. Who knows the meaning of the word osculate? No, the SATs have changed. It actually means kiss. So it's a circle that kisses the line, kisses the curve. So you create the circle, and then 1 over the radius of that circle is the curvature. Okay, so that's another way of thinking what the curvature is. Okay, it is 1 over the radius of an osculating circle. That's like the geometric interpretation of what curvature means. Okay, let me make one comment about why we use the variable s rather than t. If I have a function, say, going from, suppose I have some function sigma going from here onto, say, a donut. Okay, so at each point in time, it gives me a position on the donut. Okay. Okay, and so this is sigma of t is some position on the donut, right? If I write sigma inverse of t, then that's sort of saying like that the inverse function should have the same input as the original function. But you see that t is no longer time, right? T is actually something in space now. So one actually has to be a bit careful when you're dealing with one variable functions, one often writes f inverse of x, right? F of x is something, and then f inverse of x, you define f inverse of x, right? But it actually makes more sense to talk about f inverse of y. Yeah, really the variable that one should be using for the inverse function in the case of one variable functions is y rather than x. Okay. Okay, any questions? Any questions? I hope this makes it a little bit more concrete how you calculate the curvature and what the curvature means. Okay. Okay. So we are going to present a couple of alternative formulas for curvature. Okay. Okay. So here's formula number 1. Okay. So again, you start off with a parameterization, a smooth parameterization of some curve C, and right S is sigma of t, right? Sigma inverse of S is t, right? So this goes between the variables. Okay. To calculate curvature at position r of t, aka p of s, we examine the derivative of the tangent vector with respect to the arc length parameterization. Okay. So we have the unit tangent vector. Right? We take the unit tangent vector at the right place, and we differentiate it with respect to the arc length parameter. Okay. Now think, this t is really sigma inverse of s. Right. So let me say, what's the point here? We're going to give a formula for curvature that circumvents the arc length parameterization. Sorry, I should have made that clear. Okay, so we're going to create another formula that will allow us to just go directly from the original thing rather than going through the arc length parameterization. Okay. So we'll go from the original parameterization rather than the arc length parameterization. Okay. So so you differentiate this thing, you get, of course, by the chain rule, t prime sigma inverse s, sigma inverse prime s, right? Which is the same thing as we noted last time. The derivative of the inverse function is 1 over the derivative of the original function evaluated at the appropriate point. And so if we write this back in terms of little t, you get t prime at t over r prime t, right? In absolute value, sorry, in magnitude. So if you don't want to go through the arc length parameterization, you can create the unit tangent vector with respect to the variable that you have, take its derivative, and divide by the magnitude of the velocity vector. Okay, and that will give you the curvature. Right? So that'll give you the curvature at time s, which is to say at position r of t. Okay, I think the book denotes this as curvature r t, so that you don't confuse it with k of s. Okay, everyone sort of okay with what we're doing and how we got it, right? What we're doing is giving another way of calculating the curvature, and here's how we get it, right? The curvature is going to be the derivative of the unit tangent vector with respect to the arc length parameterization. Right? Well, let's see what that is. Blah blah blah. It turns out that it's this by the chain rule. Are you all? Is it okay or is it not okay? I'm going to take a poll because I can't read you guys. So close your eyes, please. Okay, raise a finger if I should go faster. Raise a finger if I should go slower. Okay, open your eyes, please. So slow down a little bit. Okay. So we've just created this formula. For example, if we let's go back to the circle, right? Okay, so how would we calculate the curvature using this formula? Well, say, okay, well, I want then to take the derivative of the unit tangent vector, so I need to create the unit tangent vector, right? So first let's create the tangent vector, so negative a sine t, a cosine t, right? The magnitude of the tangent vector is a, right? So I create the unit tangent vector by dividing the tangent vector by its magnitude, right? And I end up with negative sine t cosine t. Right. So now in calculating the curvature, I need the derivative of the unit tangent vector. So that's going to be negative cosine t, negative sine t. Right. Oh, whoops. So sorry, I should have put a magnitude here, right? Because the curvature is the magnitude of the change of the unit tangent vector, right? So sorry. So curvature at time t is the magnitude of this thing. Maybe that's why you all looked confused. Okay. And then, so we've just calculated the derivative of the unit tangent vector, and we take its magnitude. Its magnitude is 1, right? So the curvature at time t is going to be 1 over the magnitude of the velocity vector, which is a. So you get 1 over a. magnitude of the tangent vector, its derivative, over the magnitude of the velocity vector, which is 1 over a. Any questions? Let me, so there's a second formula that gives an alternate way of calculating the curvature, but let me throw in a slight digression right now. So digression. There's something called the Frenet frame. Okay. So, let t be the unit tangent vector. Okay. So you're traveling in outer space. At any point, you have this unit tangent vector guy that comes with you. Right? You've got your unit tangent vector. Okay. Now, I'm going to say that t prime is actually perpendicular to t. T prime is perpendicular to t. Why? Why is the tangent vector's derivative perpendicular to the unit tangent vector? Why is it true that this dotted against itself is 0?
Because the angle between them is 90 degrees.
Yes, that's the same statement. Right. Why are they perpendicular? Because the angle is 90 degrees,
No, I was answering the dot product thing.
which is the same statement.
Yeah.
Right? They're all the same statement. Why is it green? Because it's green. Because it's green. This goes back to something that we saw a couple not too long ago. Does this remind you of anything? You have some vector, and it turns out that it's perpendicular to its derivative. You have some function, and it turns out that it ends up perpendicular to its derivative. Itzel? No? Circle. It was on a circle, right?
Well,
right?
can I go back to the oscillating circle idea where you have a point and then if you create a circle around it, and basically the radius would remain constant, therefore it's always
Not so complicated. Not so complicated. Simpler than that. The point is just that, Sydney?
Is it because their magnitudes are the same
Yes.
as the unit tangent
Yes.
vector?
Yes. It's a unit tangent vector, right? So you know that all the outputs lie on a circle, right? And so as we saw earlier, right? If you have something that has a constant magnitude, then its derivative is going to be perpendicular to it. Okay. So, yeah, Melissa, I hope I haven't teased you too much. Have I teased you too much? Maybe I have. Sorry.
No,
Sorry. Yeah. My son actually gives these sorts of explanations. You know, when I ask him for an explanation, he'll tell me exactly the same thing. Now I'm teasing you further, it seems. Sorry, I should just give up, as usual. Yeah. Okay. Yeah. Okay. Yeah. better stop. I'm not gonna. Okay. So this turns out to be perpendicular to that, right? So if we take the derivative and divide by its size, and we call that thing n, this thing gives us, this thing is a unit vector perpendicular to the tangent vector. Okay. So from the tangent vector, we generate a second guy. We're going to generate a second guy called n. So the unit tangent vector, and then we get this other guy called n. Okay. This one is called the principal unit normal. Principal unit normal vector. Okay. And then if you take t cross n, right, t cross n, well, it goes into the board, but you get this third vector, right, perpendicular to it, to the other guys. This guy's called b, the binormal vector, okay, is a unit vector perpendicular to t and n. And so what you get are these three guys, t, n, and b, which form sort of a moving orthogonal coordinate system, a moving right-handed coordinate system that travels around with you. Okay. And this thing is these three guys together, this traveling frame that travels with you is called the Frenet frame. Okay. So it's useful this thing occurs in differential geometry, and apparently in outer space. I don't know if that's true, but it gives you a coordinate system that makes sense from your point of view, right? You're not going to use a coordinate system based on something that's very far away from you, but a coordinate system based on your current position. I don't know if that's true, but I heard that it's true. Okay, so and this will turn up in the homework. This has some use in physics as well, if one is talking about torsion. Okay. But anyway, we're not going to talk too much about it. Just mention. Okay, so back to the second formula for curvature. Okay. So this one is a little bit tricky. So put on your thinking caps. Okay. So again, R, let R be any smooth parametrization of some curve C. Then it turns out that the curvature can be realized as the velocity vector cross the acceleration vector. The magnitude of the velocity across the acceleration over the speed cubed. Okay. If you like physical notation, V cross A over the speed cubed, over the magnitude of the speed cubed. Okay. Whoops. Okay. Okay. So here's how one sees it. This is a little bit involved, but let's notice. Okay, so first observe that well, right, as we've said many times before, the derivative of the arc length function is just the speed. Right? The derivative of the arc length function is the speed. So maybe recall that, and then observe that then if I take the speed, that's going to be, well, the unit tangent multiplied by the speed. Right? Okay. I basically said nothing, right? The unit tangent vector is this thing divided by its magnitude. Right? So I multiply both sides by the magnitude. I get that this thing is the magnitude times the unit tangent vector. Okay? Okay. Okay, so that's one sort of simple observation. Second observation is if I take the second derivative of that, is that I get the second derivative of this guy times the unit tangent plus this thing times the unit tangent. I'll put some vectors on these guys. Some of these guys are vectors and some of these guys are numbers. Okay, so just by the product rule, right? The first guy's derivative times the second plus the first guy times the derivative of the second guy. Okay. Okay, so now let's take the cross product of the first row against the second row. Okay, so number 1 cross number 2, right? Well, that's going to be right, the first guy cross the second guy, right? But you notice what happens when I take the cross of this thing against this part of it. What do I get? If you take this thing cross this thing, you're taking a multiple of the tangent vector cross the multiple of a tangent vector. What's a vector cross itself? The cross product of a vector against itself? 0, right? So this term doesn't do anything. The only term that matters is the second term. Okay. Okay. So now, if I now notice, if we take the magnitude of both sides, what do we get? Well, we have to remember the magnitude of the cross product is going to be the magnitude of the cross product. Does anyone remember this? I'm barely remembering it. The magnitude of the cross product is going to be the well, it will be the at least we know it's going to be the area of the parallelogram, right? It's going to be the area of the parallelogram specified by these two vectors, right? Okay, so we know that that's going to be this thing times this thing. So we get a square there, and then the area that we get by crossing this against that guy. But these are both unit 1, and they're perpendicular to each other, right? So I'm going to write it like this: T cross T prime, right? We get this, right? Well, the area of the magnitude of this is just 1. Right? The magnitude of this is 1, because these are perpendicular to each other, and they're both length 1. Oh, no. Wait a second. Okay. So sorry. Hold on a second. They're not length 1, sorry. Right, sorry. So, sorry, okay, so this, sorry, let me, so what we get, sorry, is, what's this thing, right? The derivative of the arc length function, you know, that's going to be the speed, right? Right, that first thing is the speed. And then we get this, the size of this times the size of this. Sorry, they're not length 1, right? This guy is length 1, but this is the derivative of him, right? That's not length 1. Right? That's not necessarily length 1. This becomes 1. Sorry. Right. This guy is length 1, but his derivative may not be length 1. Okay. Okay. So so putting that all together, right? We see that. So we have this on the left side, we have this thing on the right side. Right? We're gonna divide both sides by this thing squared. And so we end up with r prime cross r double prime over r prime magnitude squared is equal to the magnitude of t prime. Okay, but remember our formula number 1 said that if we took this thing and divided by the speed, then we got the curvature, right? So we're just going to divide both sides by the speed, right? Okay, we'll change that to a 3. We'll divide both sides by the speed, and we get curvature at time t. Okay, so this is the second formula. It turns out to be useful. I'm going to ask you to read, you can apply this to application is to the graph of a function. So I hope to get that, but it's pretty short. Just take a look at it. Read the application of this formula to the graph of a function. It turns out that the curvature for a function turns out to be the second derivative of the function over 1 minus the first derivative squared, quantity cubed. So it turns out to be a nice formula for the curvature of a graph that follows from this formula. Okay. Sorry, I kept you over time. That's it for today. No homework due next time. The homework is due after the exam. Okay, so it looks like there's something assigned today, but don't turn it in on the day of the exam. Turn it in the day after the exam.